Here we go. Hey, Will, you want to mention our February speaker? Here, right back behind me. Sanjay.
Oh, you don't need to. Okay. Sorry.
Will, do you want to?
Yeah, that's good. Thank you. Yeah, there's okay. Okay, great. Josh, I don't know if you can check just to make sure we can hear online. Someone comments that they can. We should be. Okay, great. Thank you. All right, thanks for coming, everyone, to this month's event, final event of this calendar year. So before I announce today's speaker, I wanted to have a couple other announcements. So we have our January meeting on the 18th, decoding multi-valence light transport in time of flight photography. And on the 15th, Sanjay over here will be our speaker, discussing some of his work in subsea fiber optic cables, the underlying infrastructure that's powering the internet. I also wanted to announce quickly there's an event this weekend on Saturday from noon till 5 p.m., the first robotics STEAM Expo. So if you're interested in that, please reach out, or you can also register online, I believe, and see, I think Josh is probably the best person to go to for more details. Without further ado, tonight's talk will be by Eugene Sokolov. Thank you for coming. It'll be on system-aware PIC design for LiDAR, quantum, and telecom applications. So, Eugene, thank you.
Thank you for introduction, and I appreciate all you having me here. And thank you, New England section of Optica, for this opportunity to talk about photonic integrated circuit design, and specifically how we can make it system aware. And I will talk about a couple application examples, including LiDAR, quantum, and telecom applications. So just to make sure, yeah, we can, I'm sharing my screen, right? Yeah, so in case there are any questions in the chat, so probably also let me know. I'll be happy to answer all the questions. So, but in case, some of you are new to the integrated photonics, let maybe just briefly introduce to it, okay? So let's imagine we have some optical components, right? So that could be a laser, modulator, maybe connected with some fiber. So what photonic integrated circuits propose is actually to combine all those optical components and electrical components, in fact, on a single chip. So now you can imagine you have all this optical cable, right, shrink down to a chip of a size smaller than a dime. So that for sure great. It gives us advantage in size for sure, but it also gives us a lot of advantage in power consumption. Supposedly it will lower cost, and also it brings new functions, and we'll see one of those new functions later on. So in this simple idea actually brings a lot of advantages and have a pretty powerful impact on many areas of our life. And I got a few beautiful videos created for TED-Ed, so you can check them on their YouTube channel, created by Sajjan Saini, who is with MIT now. So I really recommend checking them out. And so one of the, I would say, primary applications for integrated photonics, which drives pretty much the whole industry nowadays, is telecom datacom, right? So communication, and so because we can really leverage those small size and decrease power consumption, especially as you see like in data centers, right? That's a huge problem. And also perform a higher speed modulation and data transmission. And although this field of telecom and datacom area remains one of the primary application areas for integrated photonics, there are other fields explored. So one of them is automotive, and photonic integrated circuits are proved to be used in LiDAR, so light detection and ranging systems. So both for just doing the measurements of the distance, but also steering your beam. Another application area is quantum, and here we can really leverage quantum properties of photons, and integrated photonics with their smaller size and very low losses could be really bring a lot of advantages here. And finally, sensing. And that's a very broad area, but you can imagine that once we are talking about smaller sizes for sensing, that's especially important, right? And that would be medical sensing, some environmental sensing as well. So I will be primarily talking about those three applications. Unfortunately, I don't have a nice example for you for sensing, but again, that's very broad and interesting area.
Would you mind just hitting the X button on the live?
Sure.
Thank you.
Here it is. Okay, so what does it mean to have a system-aware simulation? So over time, photonic integrated circuits, it's not a new thing, right? It's been developing for a long time already, for maybe decades already. And so they grew in complexity and size. And in order to streamline the design process, it's particularly important to do proper simulation. So to use photonic design automation software, right? And so traditionally, those simulations were kind of on a device level, we call it. So you actually take your device, right? You define the material properties, you define the geometries, and you start, solving pretty much Maxwell equations here. And that's very great methods, very rigorous, gives us a lot of insights into the physics of the device, but it's very hard to scale. And once we start growing complexity, we switch to the circuit level. But then, we want to test those circuits in the kind of larger complete system. And finally, the network level, the most abstract, where we purely rely on performance of the devices and not going deep into their functional, how they are organized. So we use a system level abstraction for simulating the photonic integrated circuits, our PICs. So we take our PIC and we do segmentation of it into individual building blocks, so that we can separate our device level modeling and our circuit simulation. And this gives us a lot of flexibility, right? Because one device, we can do this very rigorous simulation, solving Maxwell equations, but another part, we can just measure, right? Or just use some simplified ideal model, right? So this very simple idea gives us actually a lot of, as I mentioned, flexibility. It increases the speed and actually allows for scalable PICs design, right? So we can include now hundreds and thousands of building blocks on our circuit simulation. So yeah, that's now let's take a look what is system-aware PIC design. So that's great. We can simulate our photonic integrated circuits, and currently just some abstract circuits, right? But what does it mean to understand how it operates as a part of a larger system? And there are a few aspects here. So one is we just see how it performs as a part of a larger complete system, right? So that could be, would be our laser power sufficient, for our system, right? So or maybe our modulation bandwidth is not enough, and things like that. So further, once we estimated the performance of our chip in the entire complete system, we can probably optimize it, right? So we maybe probably tweak around some parameters of the circuit and optimize its performance. And finally, very importantly, because nothing is perfect, our integrated circuit is also not perfect, and we need to study the robustness. And again, we may try to make it perfect from a circuit level performance perspective, but probably this optimized performance is not the best from the system perspective, right? So maybe we can lose some of the requirements on our circuit and compensate it in other parts of our system. So with all that in mind, that's how the integrated workflow could look like. So we start with individual device, and in this particular case, that's a multimode interference device. So just a simple device which splits or couples two signals. And we study how it operates as part of the Mach-Zehnder interferometer or Mach-Zehnder modulator, right? And we can study how the some of the fabrication imperfections of this device impact the performance of our modulator. And after that, we can study how this modulator operates as part of the larger 16 QM system and how it propagates through a fiber and then detected. And we can see how those imperfections of the MMI actually impact on our constellation diagram. Again, that's pretty advanced system, pretty advanced modulation format, but that's kind of a workflow which we are looking into. And what it is important, it's not a one-way street. We can do our design another way back, right? So we can start with the abstract system design and work out our way down into the circuits and to individual devices, right? So we can pretty much start at any point here. So what it is needed for such a workflow to be achieved, right? So obviously we need accurate models for our integrated photonics components, right? That's something which we should take for granted. But then what is also needed for such a workflow is that we need the models also for the transmission links, right? So we need accurate model for our fiber, if we are talking about fiber-based communication systems, or we need a good model for free space optical channel. Then we also need models for transmitters, receivers. We need some signal processing elements and so on. So further, depending on the application and our system, we need characterization tools. And that's also very important, right? Because, all different kind of systems, they are characterized with their particular metrics. And some of them are pretty generic, like beta error rate or symbol error rate. Or SNR, but some of them are pretty specific, and I'll get back to this one again. This TDEC-Q, that's very specific for so-called PAM4 modulation format, right? When we have 4 levels, not 2 levels of modulation, but 4 levels. So that's very particular for this kind of systems. And again, if you do this system design, you don't want to do the simulation of how do you do these measurements, right? You just want to have them in the simulation, be ready to use, right? And most importantly, they also should comply industry standards, right? Because there could be multiple ways, so they should comply industry standards. And finally, the simulation framework itself should be in place. And this means that we need to provide a proper signal and data exchange between the components. So they need to understand each other and work under the same hood, in the same environment. And probably one of the examples for this one, if you talk about multi-mode applications, right? When you talk about multi-mode fiber, then other components should understand those modes, right? So they should understand how the overlap integrals are calculated and so on. And and there are solutions for that. That's basically why I'm talking here tonight. So the photonics and optical community was working hard to make them available. So I'm personally with VPIphotonics. That's one of the companies which provides software solutions. So yeah, sorry about this marketing slide, but yeah, I just wanted to highlight here that we've been doing this for 25 years, right? And so the field is pretty mature. So that's why sometimes when photonics world is compared to electronics world, and the photonics world is called not mature enough, I feel a little bit offended because it's been a while we've been working on that, right? Yeah, there'll be a lack of standards, but the solutions are in place and they're pretty advanced. So now if you look back at this slide of simulation level of abstraction, and there are solutions which we provide on multiple levels, including those device level simulations. But we will primarily focus tonight on the circuit level simulations on PDK, so process design kits. They stand for specific libraries for photonic founders. System simulations, right? That's where we do our system verification. And QKD, that's a little extension for quantum key distribution applications. So yeah, that was a kind of a generic introduction, what system aware PIC design looks like. So now let's take a look how this those generic concepts work and on the example, on those 3 examples. And I chose 3 very different fields for tonight's presentation. One is Datacom Telecom, and I will be discussing 200G microring modulator-based pump for link. So that's pretty state of the art communication approach we use here. And then we have some free space optical systems, and I will be talking about FMCW LiDAR systems. And finally, PICs for quantum. I will briefly introduce you to PIC transmitter for QKD systems. Okay, so let's start with what I would call pretty much conventional and or traditional application area of telecom data. Okay. And here we have simplified configuration of optical link, which describes pump for a transmission link over single fiber. So what does it include?
What's an MRM?
That would be a core part of our next maybe 10 minutes. So this stands for microring modulator. So what we got here? So we have some encoders, right? On the left, maybe we have some forward error correction. Then we have a driver, which drives our modulator, right? And this modulator encodes information into the light generated by this CW laser, right? So what we do, we basically transfer our data encoded into electrical signal into the optical domain, right? So then in the optical domain, we can transmit this data over single mode fiber and detect it on the receiver side. Okay, then pretty simple standard one. So we detect it with photodiode, we convert it back to the electrical domain, and then in the electrical domain we can do again some signal processing, equalization of our signal, maybe some digital signal processing, and so on.
So what wavelength are you using? Are you just using one wavelength?
So in this particular case, yeah, it is just one wavelength for simplicity, but obviously, there could be multiple.
Yes. What wavelength are you using?
Standard telecommunication like O-band, C-band. So yeah, coming back to the question of microring modulator, what's that? And this is why I like this particular example, because it's very specific to the integrated photonics, right? So this device, it's a small ring next to a bus waveguide, right? And what happens when light goes through this bus waveguide? It traps into this ring if there are some conditions met. And those conditions are basically the resonance conditions based on the phase accumulated in this ring, right? So if we match some particular wavelengths, then our light traps into this ring, and we'll see there is a huge drop in the transmission of our light. And as you can imagine, this is a tiny ring, maybe about a couple, maybe 10 microns, something like that, and it's very sensitive, right? So it's very power efficient in the first place, because just slightly applying some voltage, we can change the transmission drastically, right? So it is power efficient. We need very little voltage to control it. It is high speed, again, because of small size, it is high speed. Yeah, we can tune it to in a wide range of wavelengths. And yeah, it's very wavelength selective. So how we can do the simulation of this device? And yeah, we use a system level approach, right? So we have a path waveguide, and we have some coupling to the ring, right? So this one is simulated with this directional coupler here, right? Then we have some modulator section here, and then we have some heater to do the tuning. And this, the advantage of this simulation, is really because it becomes fast. Because otherwise, we would need to do the whole multi-physics simulation here. So we'll need to include electrical carriers propagation, optical light, obviously, propagation. We'll need to account for thermal propagation, to account for heating, and so on and so forth. So this becomes tremendously hard problem to solve. So yeah, and if you do the system level approach, it's fast. We control accuracy, right? So we can play around which effects to include in different parts here. And yeah, and overall, we can control our model with relatively small set of the parameters, right? So we can see some of the examples here. So this is the transfer function of our modulator. And we can see that depending on the wavelengths, right? So we can either have pretty high transmission or, pretty low transmission. So pretty much blocking the light, right? And, but we work in a little bit different way. So we fix our wavelengths. So it is fixed to 1.29 microns here. Yeah, that's the answer to the question for this particular case, right? So we fix it. And what we do instead, we start applying the voltage to the modulation section. And since the effective index depends drastically on the voltage, right? And once we start applying some, some beats here, either two-level or multi-level, we start tuning this transfer function, right? And so depending on this applied voltage, on this frequency, we will see different transmission. Okay, so that's how we achieve the modulation. So as we can see, applying this voltage, we change both the position of the peak of our transfer function, right? But also the shape, the depth of this dip. So how do we tune to a particular wavelength, right? So we may have different wavelengths, how we do the tuning. And for that, there is another section. There is this thermal section here. And, we start applying some thermal. And, and this allows for tuning in pretty wide range, right? So we can tune to the particular wavelengths. So that's how we achieve tuning. So yeah, that's just some simulation examples for this microRNA modulator. Obviously we can consider how effective index and attenuation depends on the voltage on the applied thermal shifter. We can also include nonlinear effects like two-photon absorption, and we can also account for electrical response, right? Because there is also some electronics, so this could be also accounted for. Now let's take a look how this microRNA modulator operates in the complete system, okay? So that's a PAM4 based link. And so let me briefly walk you through. So that's our electrical driver here. That's microRNA modulator we've been just discussing. Then we have a single mode fiber used for propagation. Then we have some detection, conversion to the electrical domain. We have some signal scaling, clock recovery, and so on. Then we have some equalization. And then we have some measurement tools, right? So which do characteristic. Again, those could be this theta Q, very specific for this PAM4 format, symbol error rate, extinction ratio, and so on. Yes, please.
It's a kind of paired question. So what do you need to, I guess, define each of these little blocks here is like a module? So what information, is that an actual model inside, or is there just an analytical equation that says here's what comes in, here's what comes out? And then how do you ensure that the links between these are compatible?
That's a great question, and that's basically the beauty of this approach, that you can vary. In some cases, like with this microRNA modulator, the model could be pretty much physical, right? But on the other cases, for example, for the driver, that could be very much behavioral model. You just specify the levels, the shape of your signal, right? And it just generates it just because you mentioned this to them, right? You specified that. Then the second question, how we make sure they talk to each other, that's exactly what I meant under this framework, right? So the models, they do understand each other, right? Because, for example, in this particular case, we use slowly varying amplitude approach, right? So we basically describe our signals with complex envelope. But again, that's just one of the descriptions, right? So it could be also like coarse description and so on. But that's what framework ensures, that the models understand each other. And yeah, so we can see the some simulation results here. So that's a PAM4 link. So this PAM4 means this we have apply amplitude modulation for 4 levels, right? So instead of 0 and 1, we have 0, 1 to 3. So this increases the bandwidth, more data we can transmit. And that's the signal which we obtain after the ring modulator. And here we can see the typical problem we got with micro modulator, that once we want to achieve a higher opening of this eye diagram, right? This is called eye diagram, right? So once we want to achieve higher opening, we stumble into the nonlinearities of our micro modulated response. So that's part of the problems we have. Then we may apply some equalization. It may help, right? But just to some extent. And here we can see the PDFs so that we can really hardly distinguish between those two higher levels. So that's a problem which we try to solve. And so we tried multiple approaches here. So one approach is actually we do some, yeah, so that's the first one, shows the variation of the fiber lengths. And as we expect, with larger fiber lengths, our eye diagram becomes to collapse. But we can see that, yeah, equalization kind of could help a little bit. But then we tried to kind of pre-distort our signal. So we use our modulation signal is not equidistant levels, right? So you see they're not equidistant here. So we kind of try to compensate for this nonlinearity of micro modulator. And this helps, right? So we have a better eye opening, especially after equalization. So if we take a look at the symbol error rate, it's also way higher than for the first case. Oh, sorry, but vice versa, way lower. And but the best performance is really gives us if we just choose a little bit different bias. And in this case, the eye stays pretty much open. But again, you can see how equalization helps a lot, right? And we can achieve, pretty good symbol error rate here. So that's just an example, right? So how from this tiny micro modulator, we can go up to the whole system and see the impact, right, of this nonlinearity, intrinsic nonlinearity of this micro modulator on the system performance. Okay, and that we, again, on the system level, we can account for this, right? We can play around with the bias, we can play around with the distances of our levels, and yeah, and study, maybe we can improve our micro modulated design. Okay, so switching gears to the next application, free space optical systems. And yeah, switching gears here pretty much literally. So that's a video, I don't know if you can see it well. Oh, not that well. But this video I took in San Francisco earlier this year. So this is one of those self-driving cars. Probably it's hard to see, but there's no one here, right, on the driver's seat.
Did you go down Lombard Street?
I'm not sure it could handle it, yeah. But otherwise it works pretty well, and fairly it's amazing, right? Because you sit in the car, there's nobody on driver's seat. There are other cars like that around you, and they figure out their way. And so I found it's really great. So and I'm really glad that we also work a bit with those solutions which help this kind of future happen.
So what you can push to stop the car?
I don't know actually. But probably you could. I should tell you actually. The trip, which usually takes like 15 minutes, it took 45 minutes. I don't know if they do this on purpose, so we have more time to kind of entertain ourselves. I don't know. But so I didn't mind, but if I was in a rush, I probably would. But we consider those applications which help the cars to orient in the environment as part of the broader set of applications, particularly free space optics, right? And there are multiple flavors of that. So there are terrestrial free space optical applications. So again, and LiDAR is part of them. There are also, and there are different effects which should be considered for sure, right? There are installations in the atmosphere. There are also weather conditions effects. So further, there are some high altitude applications. And again, here we have some scintillations, turbulences, but also because of the larger distances, we got also pointing errors, beam wander, and again, we have some weather conditions important. For intersatellite communication, we don't have any weather conditions anymore, so that's a good thing. But we have pointing error, and because of high velocities, we have Doppler effects, which should be accounted for. So the way we address it, again, we have a model, right? We have a component which accounts for those kind of effects, right? And yeah, again, we can see some of the parameters which it is characterized. For example, we can specify its uplink, downlink, and surprisingly, they're different, right? So if you send the signal up, or you send the signal down from the satellite, so they're different. Yeah, it is obviously, so all of the models that describe, so all the references are given. And you know,
That's a model for the atmosphere?
it is a model for the atmosphere.
Yeah, okay.
Yeah, that's correct. Yeah, for free space, I'm sorry, optical channel. Yep. And yeah, and there are some of the examples, you know, which it allows to cover, right? Like study the scintillation, how the scintillations could be mitigated in your system. Studying satellite links and so on. But coming back to LiDAR, so this is a picture of one of the cars, pretty much similar to the one I drove and I showed the video before. And one of the problems it has, and I'm sure you saw them as well, is this bulky device on top of the roof, right? And so we remember that photonic integrated circuits helps to shrink things down. So there is a great hope that photonic integrated circuit help to kind of eliminate this bulky thing on top of the roof. So let's see if it is possible. So in general, again, just to briefly introduce to this light detection and ranging, the idea is very simple, right? So we have some waveform generator, we have some laser. So we transmit the beam, we steer this beam in two directions. It goes through atmosphere, hits some object or a person, and then it is reflected back, detected, and you know, with some magic, we can get the distance and some other parameters like velocity, for example. You know, there again, multiple things to consider here. And frankly, I was amazed when I just started looking into into this field, how many there are different solutions for LiDAR. There are tons and tons. They're also based on MEMS, but for us, surely photonic integrated circuits is the focus. And one particular solution really attracts a lot of attention recently is FMCW, so frequency modulated CW based LiDAR system. So how it works, the idea is very simple. So we have a CW laser here, right? Then it is frequency modulated. So our frequency of the laser changes, right? Then we split it into a probe and reference. And the probe goes to free space, hits the target, reflected back, goes through free space again, goes to circulator, and then it is combined with the reference signal. Right? So it's exactly the same signal, but it just traveled. It got some delay, right? So we can see here, right? So since our laser was frequency modulated, right? It has some chirp, right? And it has this triangular form. It is important, but it has some delay. And once it has delay, the two electrical signals, which are detected in this balanced photon detector here, they start to beat between each other, right? And this beating could be quite easily detected. And in the RF spectrum, in the electrical spectrum, it looks as a peak. And from this peak, we can quite easily distinguish the distance to the object. Even more, due to a Doppler effect, this peak would split, right, if our object is moving. And because of this frequency difference, from this frequency difference, we can distinguish the velocity as well, right? So with a single measurement, we can distinguish both the distance and the velocity of an object. Again, it's an idealized system, right? So everything looks very perfect here. Everything works fine. However, in reality, a lot of once we start to implement this in real world, there are many things to consider. And some of the limitations come from the transmitter side, and particularly intrinsic nonlinearity of the laser. And so here we have this integrated laser design here. So what is integrated laser? It's pretty simple system, right? So we have a gain section here. We have two mirrors, but those mirrors are very frequency selective. Okay, so they have very similar selectivity to our micro modulator I showed before. And then we have a tiny phase shifting section which allows for moving our frequency, right? So again, that's a relatively inexpensive laser, and due to the fact that we have this coherent detection, it doesn't really need very high power, right? So this integrated low power solution could be quite sufficient in this case. And the rest of the system is exactly the same as described before. But what happens? We apply this triangular driving signal, but now if you take a look at our laser output, it's not linear, right? So we don't have this triangular shape form. And because of that, once we detect the signal, we cannot really detect anything, right? So once again, we see how the circuit design really impacts our system performance, right? So we have again this story, right, that very intrinsic properties of the integrated circuit, in this particular case, that's a circuit which represents the laser, have an impact on our system. And the solution is again pretty much similar as we did last time. So we can do some pre-distortion. And again, that's one of the solutions. So we pre-distort our signal, right? And with this pre-distortion, we can get to this triangular shape back, and again we can see the effect on the RF spectrum immediately, right? And we can again distinguish and get the distance to the object and velocity as well.
So sorry, what's the approximate wavelength for your LiDAR?
So for LiDAR,
Still infrared.
it is infrared, yes. So yeah, to be safe, yeah. Yep. I think in this case, it also lies in this O band.
So when you're trying to compensate for the free space, are you doing any wavefront compensation, or is it just steering?
That's a good question, and that's exactly what I'm gonna discuss next. So yeah, because previously we just discussed hitting one point, right?
Yeah.
But obviously to get understanding if it's if it's a person in front of us, or if it is a car, or if it is a building, we need to do some steering. And in my opinion, there are again multiple solutions. And in fact, this bulky thing on top of the roof, very frequently it's a mirror, so it has some mechanical parts which which have tendency to wear down. And so I think photonic integrated circuit solutions for this particular application, for beam steering, are really shine here. And that's one of the solutions, provided by those gentlemen here, a reference on the bottom. And idea is really beautiful. I hope everyone is familiar how antenna work, phase antenna work, right? So the idea is very similar. So we have multiple paths so that our phase is a little bit different, right? So the phase output of the light output from those devices are slightly different because of different waveguide lengths, okay? And this, if we could vary this phase, we can steer the light in one direction. Then we have a grating here. And again, I'm sure you all saw shell gratings in the lab, right? And if you change the frequency of your light, you can steer the light where it is reflected from the shell grating. Exactly the same principle is here. So we can steer the light in two directions, one because of this phase antenna effect, and another because of our grating. And as you can see, the circuit in this case is pretty large, right? It has already like hundreds of elements here. And that's why, we may use some Python-based techniques to create the circuit, right? To simplify this. Or we can use some kind of a graphical representation. So this guy actually represents here the whole array of waveguides here, right? So this simplifies the design, right? So that's the advantage of using photonic design automation tools, so they could simplify your design. And you can easily come from 39 waveguides here to 59 or whatsoever. And and we can see the results, simulation results. Interesting about this particular case that since we change the frequency, we change both the phase accumulated due to dispersion and also due to grading, we also steer in different directions. So you see, for example, if we follow this red line, so we actually steer in both directions simultaneously, okay? And field of view in one direction is good here, but another direction is relatively small, just a couple of degrees. So that's why they actually use multiple devices like that. But again, multiple devices mean that we need like 4 times more elements on our circuit. And and to perform this full-fledged 3D scanning, it's really very important to have a fast simulation, right? Because even if it takes just a couple seconds to do, let's say, 100 by 100 a scan, it means that we need, I don't know, a couple hours of simulation, right? And I did math beforehand, so it's not like I did on the fly. Yeah, it's like 2-3 hours if you just have like a couple seconds of simulation. And so it should be really very robust fast simulation. And here we can actually see the results of a study. I'm sorry, just get back real quick here of this free space here, right? So this guy allows for studying weather conditions, and we can actually see how the picture changes if we have some fog, thick fog, or dense fog. Okay. So once again, just to wrap up here with this application example, so we have again this integrated circuit either for beam steering or for light emission, and it has direct impact on the overall system, and we need to account for the restrictions of our circuits.
So what do the different colors on here mean? That the grayish means it's closer?
Yes, yeah, it means that it's kind of a depth map.
Yeah.
Which we obtained. Yeah.
So it's going from gray to orange.
Yeah, the orange is closer, and blue means like further away. Yeah.
So on the right, that looks like a picture, but is that actually like a 3D rendering that's used as an input to this model?
That's a great question. So we in fact we don't use this particular picture as an input. We use a depth map obtained from this picture. Yeah. But that's a great comment. Yeah.
So are most of these modules hand designed by the users, or are they things that already exist as part of your software package?
Both, actually both. Yeah, some of them exist. For example, for beam steering, there are some custom solutions here. Yep. But for example, waveguides, all this part for sure they exist. Yeah. Okay, luckily we have some time for the last example, and Shakir should ask, are there any experts in quantum communication? That's the answer I expected, so that's great. I'm neither. I'm not an expert here as well, but I'll do my best and guide you through some of those examples. So probably you know that, sorry, just need to switch this off. Probably you know that with recently all this buzz about quantum computers and that our existing security system is jeopardized because the algorithms we are using for cryptography, they could be broken, right, with more powerful ones like those quantum computers. And so there are the whole movement, and again, it's not new, it started like in the 80s, how we can overcome those limitations of that existing cryptography, and there are some ways of doing that, and one of them is quantum key distribution, right? So basically, this means to use very fundamental quantum properties of photons to transmit the information between different parties. I'll explain this a little furthermore, but before that, I just wanted to mention this unicorn project which we are part of. So this is a project sponsored by the European Commission, and it includes multiple parties, including universities and also integrated photonics foundries and also commercial companies. So we are here participate on this design automation and simulation part. And the purpose of this project is actually make those quantum key distribution algorithms and solutions available to public, right? So to make them inexpensive and accessible. And what I really particularly like about this slide, in fact, is that this project stands on these 4 pillars. And if you remember the slide I was showing at the very beginning, with different level of abstractions, it repeats pretty much identically, just flipped, right? So one of the pillars is actually designing of the integrated circuits, right? Another is integration of those circuits into the system, then into the networks, and finally there is a pillar of or aspects of the protocols. So we are mainly participating on those 2 fields, on designing photonic integrated circuits and doing the system integration, but also a little bit on these quantum protocols. We don't really develop them, but they could be tested in our system environment. Again, just I'll do my best to be very short, and because things get complicated here very, very quickly. So, what we know about communication, right? So, for example, we have this Alice and Bob communicating through classical communication channels. That's the channel we're using right now, okay? And what happens if there is some eavesdropper, right? Listening to this communication. For Bob, it's pretty hard to detect this, right? So we probably will see some attenuation of our signal, but other than that, it's hard to tell. And all our security currently relies that for this Eve, it's hard to break the code, right? But if the code could be broken, then our communication is also broken and all the data could be decrypted. What is proposed to do instead? Instead it is proposed to share the key, right? Which we use to encrypt our information, to share it through quantum channel. What quantum channel means? So quantum channel means it's just completely different ways of sharing the information. And I would just scratch the surface here. And so it uses very fundamental quantum properties of photons. So one of them is actually that our photons could exist in a superposition state, right? And this superposition state, for example, means that we don't really know which particular polarization our photon has, right? And we don't know this until we actually do the measurements. And this measurement actually breaks our superposition, right? So it collapses our superposition state. And the important that it doesn't matter who does the measurement, who did the measurement, and it could be done only once. So saying that, if somebody does the measurement, if somebody interferes, then Bob could actually distinguish that and break the communication, for example. Another actually, and this used for different protocols, is actually using quantum entanglement. So we have 2 photons there, right? And again, if one is measured, then we definitely know what's another photon state is, right? And based on those, I would say 2 principles, those quantum key distributions algorithms are based. Again, things get complicated very quickly. We need to account for components imperfections, so there are some non-linearities in our fiber channel, for example. Again, we may operate not with actual photons, but some weak coherent states. We need to account for Raman scattering. Again, some very specific characteristic like the dark count rates should be studied, and so on and so forth. Again, there is a whole field which we need to study. And to address that, we actually created this little toolkit, maybe not little, but which actually does solutions for that. So it provides the transmitters, it provides the receivers, it provides the analysis tools, because as you can imagine, there are always other ways of characterizing those systems, like measuring not BR but QBR, and there are all a set of protocols which are implemented. So the whole field. And so here's another examples, because there are also different approaches, like for discrete variable or continuous variable. So those are components for this discrete variable. And actually somebody mentioned there was a talk about a single photon avalanche detectors, right? So those are really important here because we try to detect just a few photons, and those are pretty expensive. So that's why actually those systems, sometimes criticized because of the complexity of this approach. But again, there is model for that. There is whole range of effects included in this model, which is very, very specific to this. So within this project, there was a circuit transmitter, coherent source for QKD systems developed. And so we can see here the brief explanation of the system. So we have this source of coherent states, and that's again just photonic integrated laser. So we have a phase modulator to encode our data, pulse culver, and then we have optical attenuator, so to get our photon flux down to just a very small number. So that's actual tunable laser, which we can see here, and that's a picture of actually fabricated device. Okay. And in fact, this structure is kind of similar to the one I was showing for LiDAR, right? So we can see again some amplification section, some DBRs or mirrors here, and there's some modulation section to do the tuning. So here we can see some comparison of the simulation results, and that's the whole system, right? So Alice prepares some states, and again, for example, in this case, we are using this BB84, one of the I think one of the oldest, simplest protocols, and then the information is encoded with this phase modulator, and then there's pulse cover, so pulses are formed in this mugs and the modulator here, and then we have a three-stage cascaded set of interferometers to actually get our photon flux down, and and then we coherently detect the signal, and we can study, in this case, very simple study, what would happen if our phase modulation isn't perfect, right? If we do modulation not plus minus 180, but have some 5 degrees error, right? So, and we can see what is the difference. And then we can perform the measurements. As I mentioned, one of the figure of merits for those kind of systems is QBR, and we can study different alternatives, right? So what if our system is ideal? What if we do some realistic tuning or realistic detuning? And I was told, again, I don't know, but I was told that those numbers are still pretty high, and this means that we need to account for more effects on the in the system, most likely on the receiver side. Okay, so yeah, fairly speaking, yeah, all of those examples are available on our YouTube channel, so subscribe, thumbs up. Yeah, so you're most welcome to explore them, to get more details about the applications I was talking about. Yeah, if you have more questions, yeah, please feel free to reach out to me via my email. And yeah, and just to wrap up, I just want to encourage you. So if you are looking into the field of integrated photonics, you definitely should. I genuinely believe that's the future for many optical systems. And if you do your PICs design, please consider doing some system validation, right? So try to take a look on a broader system, not just focus on this circuit performance, but just try to see how it operates in the complete system, and maybe try to optimize this from this perspective. Yeah, that's what all I wanted to show. Thank you so much. Yes.
Yeah, are you working mostly with corporations, or do you have a lot of academics? I noticed in that consortium, it looked like there were quite a few sort of academic institutions.
Yeah, absolutely both. Yeah, absolutely. Yeah, we work both with corporations, big corporations, but also with the universities. Yeah. Yes.
Is there a reason this, I guess this type of simulation is limited to PIC design? It seems like it'd be pretty broadly applicable to PIC applications, for example, like just general free space optics or other design. Is there a reason that you're particularly focused in that space?
Yeah, the only reason why this why I focus because that's my field of expertise. Probably if other guys from our company would give a
Oh,
talk.
Understood.
You won't get this impression.
Okay.
Yeah, for sure. And in fact, I should admit that most of our customers they actually working on a system level,
Got it.
and that's going down to a circuit design level is just an option for them.
Got
Yeah, more physical questions.
I guess the other question I had is if you're simulating, a lot of times when you're simulating something and you actually build it, you find out that what you build doesn't necessarily meet your sim. There's some weird interaction that you're not anticipating. So if that type of thing occurs and whatever you're actually building doesn't match the simulations, how do you kind of reassess your simulations, or are there ways to kind of resimulate or incorporate those new learnings from things you actually see in implementing it?
That's a good question. Yes, but frankly, it happens usually a little bit differently. So usually, how very common story. Somebody does implementation of the system or a circuit, and it doesn't operate as they expected. And then they say, okay, we probably need to do some simulation. So they frequently this first step is missed, that people first do the simulation and then they do design. But then still things, it's not easy for sure, right? And especially if we talk about like laser design, there are tons of effects going on there, right? Which could be accounted for. Or for example, this microwave modulator, what frequently happens, some of the effects are not included, and I deliberately mentioned this that like non-linear effects. Sometimes we just emit them, but then something doesn't work as we expected. So probably we need to account for those non-linear effects like two-photon absorption, for example. No easy way, right? But the beauty of simulation, you can switch the effects on and off, and you don't need to kind of switch them all at once, right? And get a mess, but you can start, pulling the triggers and see what would lead to the effects you see in the experiments, for example.
So is that just comes at a cost of higher computation time the more you're kind of turning on, or?
Sometimes, yes. Yeah, very frequently, yes. Because, for example, even this microwave modulator model, there is a simpler model, which just a behavioral model reproduces this curve of the transfer function, but you won't be able to go deeper into details like this two-photon absorption, for example, right, or other effects of interaction inside of your waveguides. But there are surely limitations as well, right? Because those are all compact models. You cannot, for example, change, again, coming back to this microwave modulator, if I switch back to it. Okay. Show and so, for example, this one. Yes, you can include some of the effects right in the waveguides, but for example, you cannot really change your PN junction design. You rely on some maybe other simulation which was done for this PN junction and which says you how your effective index depends on the applied voltage, or you rely on the measurements. But again, that's something which you not really include in this circuit level simulation. Maybe we have some questions in the chat. I don't know.
Nothing so far.
Okay.
Yes, actually, we have one. So for FMCW LiDAR, is there any noise modeling by atmospheric condition by MATLAB or other co-simulation platform, please?
So yeah, in the first place, we have the model, already implemented, right, which includes the noise. But the answer to this question, yes, it could be done. Yes, in fact, we worked both with Python and MATLAB. So if you have your own in-house models, then you can quite easily get them software, for sure. But I think. Again, I'm not really very big expert in our free space optical solutions, but I believe that the model we use is actually based on the kind of models which are accepted in the industry, right? And there are models which describe like attenuation of your signal based on the weather condition, for example. So there are some kind of lookup tables and things like that. Yeah, yes.
No, do you guys do any like tissue type models?
Very like on a shallow level. I think there was also a question.
Yeah, telling off of David's question, I was curious with this micro ring modular photonic integrated circuit design. Have these transitioned into like data center applications? I'm trying to understand like how ubiquitous these PICs are.
That's exactly the application, yes. So data center, and because especially for data centers, you know, the huge amount of data is actually transmitted inside of the data centers. I think like a third of the whole traffic is just inside of the data centers. And for them, the power consumption is a big of an issue. So that bringing down the power consumption of the modulator could actually make a lot of difference. And so those PAM4 modulation formats and using micro modulation for the modulators for that is definitely an application for data centers. Yes.
So given those benefits, have they formally manifested in quite a bit of the data centers, or are they still kind of, hey, we see these benefits? And yeah.
I think actually it's already been rolled out in the data centers. Yes. Yeah. So it's happening. I think it's past this research stage, or that it's actually started being deployed in the data centers and in the systems. Yes. Yeah.
Yeah.
Yes.
How much do you have to tinker with your models? In the sense that you sort of look at this list of parameters and you put in something realistic and it gives you something right out, yada, or are you, say you already have one output that you're trying to match with the parameters you have? You know, how much, like you plug it in once and you go, or how much process is in there? It's not a very well formed question, I know.
But you know, I had actually an interaction with one of the customers, and who was very experienced in the laser design. And I always thought that setting the parameters of the laser design is just it's very hard, right? It's a tremendous amount of time. But you know, I got to this guy, and he was great, really. And it took for him to set up all the parameters like on the fly, because he knew the stuff, right? So I think my answer is it actually really depends on the experience of the person, right? You know, if somebody really knows what's going on, it's not such a big deal. But if you're learning yourself, right, and if you are trying to figure out what's going on inside of this PIC or the laser or the system, right, it doesn't really matter, then yeah, it may take some time to set the things right.
Well, you'd have to do like a tolerance study. You'd have to do a tolerance study,
Yeah.
you know, for whatever your process is, you know, so all the variables are gonna have.
But that's already like when you have already set up, right? Then you can switch kind of to the tolerance studies, because what happens actually many times, and that people try to kind of switch on everything they have, right? Like let's put the fiber right away and all the effects and the chirp and the laser, like just everything, just to make it as realistic as we could. But that's not the right approach. So you always should start with simpler models, right, and increase the complexity gradually. In this case, you understand what's going on, right? You know that, for example, your MMI device that I was talking about at the very beginning. So, for example, very simple fact that this MMI, it splits the light, but not equally. Very simple effect, and obviously in any MMI you will fabricate, you will see that. But what will happen, actually it has a pretty tremendous impact on the extinction ratio of your Mach-Zehnder modulator, right? It's very simple, and you know, if you just switch it, and then this extinction ratio has direct impact on your constellation diagram. And again, if you just switch on everything at once, you would. It's kind of very hard to understand, you know, what this blurring of your constellation diagram comes from, right? So but yeah, if you do this in other way around, if you first put your system, right, and have you, for example, MMI here being ideal, and then, okay, now I switch on some more realistic effects here, and then you see, okay, here's the impact, right? And then step by step, you can approach to more realistic simulation results.
So you had several plots, like the eye diagram you showed an example. You run through the simulation, you look at the results, you use that to like intelligently adjust some part of the model and then run it again. How much analysis would this approach is sort of done that way? Or would you potentially do analysis, where you've got many inputs? Would you run like a Monte Carlo type of simulation to kind of search out the design space? And then go from there, or?
I mean, it really depends. I mean, any approach could be used, yes. Especially if like we do tolerances analysis or yield analysis, then yeah, Monte Carlo simulation is definitely the way. There could be just optimization techniques, right? And again, there are multiple optimization algorithms. In fact, there are machine learning approach, right? So we can actually replace the whole model with a deep neural network counterpart.
I'm sure you could just kind of, even with a neural network, you could discover some potentially interesting effects for applications somebody may not have even. So,
Yeah, I would say, yeah, pretty much.
with a complex enough system.
Yes,
In both devices, there in optics, there are gradient index effects. Is that not an important thing in this because the device fabrication is so good in the foundries that you don't have to worry about small changes in the index of refraction of the optical components?
In fact, you do, yeah, you do need to account for this, absolutely, yeah. And especially if we talk about system like this Mach-Zehnder modulator, right? So just a small variation between an effective index between your two arms, again, it leads to changes, and we kind of see it here, right? But you see the results are not like ideal. There is some tolerances, there's some deviation in the transfer function of this Mach-Zehnder interferometer or modulator, right? If it's real at steady state. But what happens in fact, if you have those variations and just enough very tiny variation, and your picture starts completely like shifted. In fact, this is already optimized. If we just do this realistic simulation, we would get here just a full covered picture with transfer functions. What is needed, and what is usually done, there are little phase shifters in each side and each arm of the Mach-Zehnder interferometer so that we can tune and compensate for those kind of imperfections. But they're definitely important. And in fact, I would say that the effective index properties, dispersive properties of the waveguides is something which makes it very different from the electronics world, right? Because in the electronics world, we connect components with wires, and in the first kind of approximation, we don't really care about those wires, right? And the effects going on inside. But in photonics world, the waveguides we use for connection, they actually functional. They actually introduce those phase shifts, group delays, and those are inherent functions of those devices, like in this Mach-Zehnder interferometer, right? And so accounting for those phase variations is definitely important.
Josh,
Yeah.
any other, nothing else on Zoom, so.
Yeah.
Thanks very
Again,
much.
thank you so much. It's really pleasure.
I never really